I want to start first by asking you if you have any questions. So I see Alicia, Carly, and Tanisha. Central limit theorem. Okay, we can go over that. That's the last section in this, so I kind of want to stay on track for order, but I promise that I will cover that, and we'll do some examples. Okay, oh, let me go to chat. Okay, central limit theorem, and again, everything. Oh, okay. Well, that's good. I'm sorry.
I know how that feels.
Yeah, I do too. But I think on this week everybody's overthinking it again. So I'm just gonna go ahead and get started, and you just chime in anytime. No, don't raise your hand because I can't see when people press that raise hand button. Just either talk or chat, and I'll get your answer. I'll get an answer to you right away. Okay. So again, I'm recording this, but let me just start. And this whole, I have to get used to writing on this again. The normal curve, okay, and let's start with the standard. Now, what makes a standard is that the mean is 0. Now, never in your life, probably, are you going to have a mean that's 0. Okay, so that is why we have a normal curve, and we use the z-score to go back and forth. So I'll draw a picture of that in a minute. Okay, 1 standard deviation away, 2 standard deviations, and usually there's not more than 3 because you're getting to the tail end. Now, not many things really in real life follow a standard normal curve, or even a normal curve. Things like height, weight, IQ, things like that follows a normal curve. But I have to make it clear that there's other distributions, okay? We're just learning one of them. So if you go left, that's -1 standard deviation, -2 standard deviations, and -3 standard deviations. Okay, so I'm going to draw a normal curve underneath here. And a normal curve is, again, like heights, weights, IQ, things like that. They all follow a normal curve. Now, again, I said the mean wasn't 0. So the mean can be anything. And what we do is we use the z-score, translates it back to the standard normal curve. So the z-score translates it back to where the mean is 0. And a z is x, which is your score, minus the mean, divided by the standard deviation. So this formula right here translates the normal curve that you might have into a standard normal curve using that formula. So like I said, our mean can be anything. Now, let's take a mean of 24, and the standard deviation is 5, say. If you move over 1 standard deviation, you're going to be 5 units over. You'll be at 29. So this is +1 standard deviation on the standard normal curve. Then you keep moving over by 5. So +2 standard deviation would be 34. And then, again, you don't go much beyond 3. That takes almost 100% into consideration. 39. So on this graph, you're translating what you have, I'm just making up an example, into the standard normal curve where this is 0, 1, plus 2, plus 3. And then if you go this way, it's minus 1 standard deviation. So what would that be? That score would be minus 5, so that'd be 19. Minus 2 would be 14, because 5 is our standard deviation, and then minus 3 would be 9. Now, why do we want to do that? Well, we want to do that because that comes from a very, very complex mathematical formula from calculus. We don't have to know the formula. All we have to know is there's something called a z-table, which I had to use when I learned this maybe 20 years ago, but now we have technology and we can use calculators to determine our areas. So probability, what does this have to do with probability? Probability is the same as area under this curve. They're exactly the same thing. So say you want the probability that your score is between 19 and 29. We can find that out really easy. So I'm going to show you 2 ways on how to determine probability, because this is what these curves are used for. Okay, so that leaves us, again, I'm just quickly going through all you need to know about normal curves. The empirical rule. It turns out that on every normal curve, between minus 1 and 1 standard deviation, this area right here is 68%. Or the probability that your score is within minus 1 and plus 1 standard deviations is 68%. Between minus 2 standard deviations and 2 standard deviations, it's 95%. Now, this is not exact. This is just about. Okay, but it's a quick way to determine probabilities. And if your score, the probability your score is between minus 3 and 3 is 99.7. So see why we don't go beyond 3, because that's almost 100%. This whole area under this curve is 100%, or 1. The probability that you're somewhere under this curve is certain in these problems. So the whole curve area is 1 or 100%. Now, I think I'm going to just go right to an example, and then I'm going to let you ask a question, because that's all you need to know in this whole deal, pretty much. Because here's what we're going to do. Here's my problem, and I'm going to go slower so you can help me answer it. All right, suppose we have light bulbs from a certain company. Their mean life, that means how long they last, is 1,000 hours. Their standard deviation is 100 hours. What is the probability a bulb lasts at least 1,200 hours? Okay, and then somewhere in this, it would say normally distributed. Life of a bulb is normally distributed. Again, there's many, many, many distributions. We're just learning one of them. Okay, so does that look familiar, like something on your homework? A problem like that?
Yes.
Yes. Okay, good. Good. All right, so let's draw a picture. There's not a lot of pictures in the material. So here's our normal curve. You should always, in fact, you should always draw a picture for every problem you have. It'll help you see what you're trying to find. Our mean is 1,000. And so if you move over by, let's say 1200 to 1200, what does it mean when it says at least 1200? Are we going to go smaller than 1200 or larger than 1200?
Smaller?
1200 and up.
Yeah, 1200 and up. At least means that's the minimum. At least is minimum. So this really means greater than 1200, or it could be 1200. That's not going to matter in the problem. So that might be another issue, like the wording. You have to really be careful about what it's asking. So when it says at least, it means that number or more. That means minimum. So the area we're looking for is right here on the normal curve. We're looking above 1200. Now, I don't know what calculator you have, but if you use the online calculator, and I'm going to go to it right now to show you, so I hope I don't lose anybody. I'm just going to share my screen.
It's not up to the 1200?
I'm sorry, what?
I said, so it's not up to 1200, so everything
No, it's
below
past
1200?
1200.
It's past 1200.
Yeah, at least means larger than 1200. That's the very least you can have. It's a minimum. So that means everything it's greater than. At least means greater. I know that's weird, but at least is the minimum.
Have you found some kind of a cheat sheet online that helps to break those terms down to, I mean, I know is equal, at least, greater than, you know, and so on?
No, because that's different for everybody.
Okay.
I mean, it's different of what people know and what they don't know, and I haven't put anything together like that. I mean, I could think about that. Like at most, what does at most mean? If it's at most 10.
I'm thinking if it's at most, then it's going to be everything below. And if it's
Right.
at least, it's going to be everything above.
Right.
Okay.
Because at most is the maximum. That's the maximum
Right.
it can
At
be.
most, yeah. That makes sense.
So, and that would always be true. Okay, so I'm going to go to this online calculator. This is the calculator that I link to, or that the material links to. And in this, can you see it?
Yes.
Okay, I don't want to lose anybody, so just it's not rude to stop me, because I don't know when you have questions, so just stop me. The mean's 1,000 here. That's all you do is type that in. Standard deviation's 100. And then which one of these do we want? For the light bulb problem. Above, below, between, or out?
Above.
Above, yeah.
Above.
1200. So you just type above 1200, and you're going to calculate that. You want the area, which is the same as probability, so it's 2%, 0.0228 or 2.28%. Okay, so don't be overthinking these problems. That's the answer.
The use of that calculator, I did the learning check on this last night, and the use of that online calculator makes it much easier to get a visual representation of what you're doing.
Right, you have to either draw the graph or get the picture here, because this shows you, that graph shows you that it's greater than the 1200 at this tail end right here. Now, I can ask questions on this all day long. Let me go back to my board. Oh.
Can you, when you get a chance, can you show an example of the inverted normal distribution where you're finding percentiles and stuff using that
Oh yeah, I'm
calculator?
gonna do all that too. Right, I'm going to do all that too. I do have an example of that. So that's why I said we can use this example all night long, and I can do an example with percentiles. So
Okay.
first let's just do how long will it last between 800 hours and 900 hours. Well, you just go to your calculator, and this time you just want between, and I don't have to change the mean or standard deviation. It's the same problem. I just type in between 800 and 900. And this is so much easier than the table. It's not cheating. See, and then look at, you get a picture. The area between 800 and 900, the probability it's between those two is 13.6% or 0.136. Now in the homework, you have to make sure what it's asking. It might just, if it's asking for probability, it's going to just want the decimal, the 0.13. If it asks for percent, then it would be 13.6%, but that's the same thing. So just be careful what it's asking. Okay, and then what if we want it less? The probability the light bulb lasts less than 750 hours. Tell me what that answer would be for this
Then it would
problem.
be in the below.
Yes. Yeah. So don't make too much more out of this. It'd be below 750, and then recalculate, and you get 0.0062. So it's almost zero probability that it's going to last less than 750 hours. Well, that's good to know, because you know you want to buy this light bulb and make sure it lasts. So that's a good thing. Okay, so that's all you have to do for probability or area, is use this online, and this is that online normal calculator. Areas under a normal distribution. Now, you asked me about the percentile, so let's do a problem like that. Let me go back. Let me go back to the whiteboard, and okay, here's a problem. Say you have a class of boys, and they're doing push-ups. So the mean number of push-ups, say, is 50 for the whole class. That's the average number of push-ups each boy can do. And then, I mean, you can have girls in here too. It doesn't matter. I don't want to be sexist, but the standard deviation is 10. So we have a mean of 50 and the standard deviation is 10. Bill says he can do more push-ups than 90% of the class. And again, you have to do, somewhere in the problem it'll say normally distributed, and that means it follows that bell-shaped curve. So this is asking basically for the 90th percentile. What is the 90th percentile? Because he just has to do one more than that. All right, what's the difference between this problem and the one we just did? Well, the light bulb problem was asking for probability. It was asking for the area or probability. It was asking for the percent. This is how you tell the difference. If it's asking for, if it's giving you a percent, that's when you use the normal, inverse normal, because you want to go backwards. We know the area. We want to find the number. before the last problem, we knew the number and we wanted to find the area. That if they give you a percent in the problem, then you use the inverse normal calculator.
So are you calling the area the 90th percentile?
Yes.
Okay.
Because, well, the 90th percentile is a number. Sorry. But 90% is also a the answer to the 90th percentile is a number. But the 90th percentile represents the point where 90% are below that point. That's what a percentile represents.
Isn't it going to be the shaded part underneath the curve? So in that, if it's the shaded part underneath the curve, the way I understood it, and then that would be considered the area. So you would use the inverse link that you give to plug in the area, the standard deviation, the mean, and so on. That's how I understood it.
That's exactly right, because the 90th percentile is your this time you know your area. You're trying to find this number right here, this x value that goes with it. Before we knew the x, we knew it was between, say, 800 and 900. Those are our x values, and we wanted to find the area. Now we know the area, and we want to find the x. So we go to our normal distribution, inverse normal distribution. So this is the inverse problem. We know the area is 90. So we type in 0.9, or you could do 0.9, whatever you want. The mean's 50. And the standard deviation is 10. Now it showed above because that's not what we want. The 90th percentile is below. We want to know where that number is right here. So you have to know the definition of percentile. That goes back to week 1. In week 1, where we had to find that number that represented a percentile, was everything below that. And that's what our graph says. So you have to know percentile means the area below a certain number. So this came out to 62.8. So this number right here on this graph, right here, by the 60, is, he'd have to do how many push-ups to be above that?
Man. Yo.
How many push-ups would he have to do to be above that?
63.
63, yes. Well, great. Yeah, you got it.
That's right there, yeah. So this is what threw me off. This is when we were doing the homework. When I was doing the homework, this is the part that was throwing me off, is when it was saying it wanted the 90th percentile, or the, I don't know, just number off the top of my head, like the 52nd percentile or something like that, is determining what section is the correct. Is it always going to be if they're asking for percentile, they're asking for everything below, correct?
Yes, that's the definition of percentile.
All right.
That comes from the definition of percentile. Percentile means below that number.
Got you. All right.
So I had other people ask me about the IQR, okay, because I know in one of the homeworks it's asking for the interquartile range. Do you remember from week 1 what that is?
Well, is it the interquartile range? Isn't that be considered the 50% range? Because isn't it? Well, no, it's going to be the 75. Subtract the 25th. So whatever value is that left is it.
Yeah, or it could be the middle 50%.
Yeah, middle 50%.
So you write either way. We'll do it either way. So you take the 75 and you subtract, because it's the middle. I don't know what that is. Okay, it's the middle. Here's 25. Here's 25 area. and here's the 75% area. So it's actually your middle 50. So again, when you're dealing with percents, you're going to go to the inverse normal. Okay, so you're going to go sorry, I want to share the screen. I keep messing up. Okay, screen. Okay, and go. There are 50 push-ups was the mean, or the area. Sorry, the area is the 50. So let's just do 50. Mean is deviation is 10, and you want it between. So.
Oh, okay.
This is just one way to do it. I'm going to do it both ways. So what you're going to do now is subtract those two numbers. Because a range is one number. The range is how far apart are those two numbers. So it's going to be something like 7 and 13, 13.5.
Yeah, that threw me. That took me for a little bit to figure that out. That they weren't looking specifically for. Yeah, I see it in my head. It's hard to put in words.
Yeah, it is. Math is hard to put into words, but we can do this. We can do it. Okay, see, if I did below 25%, I got that second number. 56.7 is the same number we just got was between. And then if I change this to 25, I should get 43, which was my other number. There we are. So you could do it that way. You could say, what is the area between the 75 minus the 25th percentile? And you could do it that way. But I think it's just easier to do the middle 50 and do it between. And we get the same answer. Because the definition of inner quartile range is between 75 percentile and 25th percentile.
So you subtract those two numbers to get the actual IQR.
To get the actual range, yes.
Okay.
Now, if they just asked you 75th percentile, then you would go 75 here and do it below 75. Remember, percentiles below.
Right.
So you would get 66.7. That would be the 75th percentile.
Okay.
And the problem I looked at is that it asked for the middle 30%. So how would you do the middle 30%? So again, the problem's asking you for percent, so we would use the inverse normal. So we would put 30% in for our area point, and these always have to be decimals. The area under the curve is 1. And then we do between, because we want the middle 30%. And it does it for us. And these calculators online are just so amazing. I mean, I just can't tell you enough how easy this makes it, because a long time ago you had to use tables and you had to interpolate, and it was messy.
Now,
and again, you're subtracting the.
Go ahead. Sorry.
No, if you want, no, this is not in inner quartile. This question I was basing it on one of them in the learning checks. It asked for the middle 20%.
Mm-hmm.
So I'm doing the middle 30%.
Okay, so you have it would say on there between each of those values. Yes. You'd write about. Okay.
Yes.
That's how I did. Okay.
It would ask you for two values.
So if it was asking for the range at that point in time, we're going to subtract the two values.
Well, that wouldn't be the inner quartile range, though, because the inner quartile range is the middle 50.
Right.
But
Okay.
if it just asks you for the range, yeah, you would subtract those two.
Okay.
Just be a little careful there.
Yeah. Oh, I figured that out.
Okay? Okay. Well, you still have a sense of humor, so that's good.
You got it to get through statistics.
Oh, I know. In 6 weeks, no less. Okay. I was just going to mention one other problem that somebody asked me about, so I want to go back to the whiteboard. Okay. Let me draw a picture. And again, if you have a normal distribution, that's this bell-shaped curve, the area under this whole curve is 100% or 1. So the probability that something is under this curve is 1. And then I think a lot of people, again, were overthinking this. How about if we said the area to the left is, say, 0.3. Then what's the area to the right? The last question in 3.3, yes, I can. I'll go to that next. We'll talk about the last question. So I had a lot of questions on this question, and this number could change right here. It doesn't have to be 0.3, whatever it is, it doesn't matter. So if the area to the left is saying the area to the left of your point is 0.03, okay? That's your picture. That represents this probability or area right here. Then what's this right here? What's that area?
It's going to be whatever that 1 subtract whatever that 0.03 is going to be.
Yes, that's all it is. That's all they're asking. They wanted you to know that the area under the whole curve is 1. So the area to the right is just 1 minus 0.03.
Or
I mean,
100. Yeah.
It either has to be the left or the right. Because the total is 1.
I had a question, and you might be covering it already.
Okay.
But it's interpreting the P. Let me read out kind of in my head. It's going to be P open parenthesis X, which is greater than a number value greater than, and then a close. It's interpreting the numbers to plug into that equation, and I'm actually using my phone to see this, so I don't even have I'm sitting in my truck at work, so.
Well, so you're saying it was a problem that said P with parentheses X greater than some number parentheses equals a number?
Yes, it was like P. It was like do you see what I'm saying? It's
yes.
It's P open parenthesis X greater than some number close parenthesis equals the probability, I believe.
Yeah, yes. I mean that's what P stands for.
But inside of your parenthesis, you will put another greater than symbol and then another number.
No. I mean, this would be a specific number like 0.7?
Yeah. And then another if you erase your parenthesis equal and then that probability and then put another greater than symbol and then put another number and then close parentheses. So there's two numbers, two greater than symbols.
No. I think you're doing this. I think you're saying like maybe 10 is less than X less than 20.
Yes, exactly.
That means between.
Gotcha.
So on your calculator, you're going to do between. So,
all right.
Because it says X is less than 20, so here's 20. So X is less than 20 on this side right here. And on this side, it says 10 less than X, but if you just switch it around, it's still pointing to the 10. That means X is greater than 10. So here's 10 and X is greater than 10. you're saying between. So anytime you see something like that, that means between.
All right.
So you're going to just use that in the calculator, and you're going to, which calculator are you going to use? Are you going to use the normal or the inverse normal? If we want to find the probability.
I think I would use a normal.
Yes.
Yeah.
Yes, because we have the numbers and we're trying to find the area.
Yeah, in the between, yeah.
So we're going to use the normal calculator.
Gotcha.
Okay, let me see the last question in 3.3. I have homework printed out, and then I need to get to the central limit theorem. Somebody asked me about that, so I want to cover that. But main thing is make sure you know which calculator you use, because they make your life so much easier. Okay, well, it's the same. The last question in 3.3 is the same as what I've been going over. So I'm not going to do that problem, but I will do another one like it. So let's say we have, I don't know, maybe let's go fishing, and our mean fish length is 16 inches, and the standard deviation is 2 inches. So let's just do a couple problems like this. The probability that the fish is greater than 19 inches. Now, while I'm going to give you a chance to work this out, if you could get to your computers, and if you have a calculator. If not, I'll do it. But while I'm going to give you time to work that out, the last question in 3.3, and I'm not trying to stop from answering it. I just want you to think a little more about it. It says, these are CD players, and the life is 4.1 years, and the standard deviation is 1.3 years. It's guaranteed for 3 years. Find the probability the CD player will break down during the guarantee period. Well, so if they're guaranteed for 3 years, you want to find the probability that X is less than 3. So it's the same problem that we're working on right now. That's the first. This is number 13 in 3.3. Okay, fish. Let's do the fish one. Let's go back. Now I want to share my screen. And I'm going to say the mean is 16. The standard deviation is 2. And I want it above 19. And my answer is 0.0. That you can erase that 750. We don't need it. It's 0.0668. So I would say that's about 0.07. Sorry, I can't. So on that one, we use the normal calculator. Okay, on the last one in 3.3, it also asks for the 70th percentile. So let's do the 70th percentile here. What did we say percentile means?
Below the number.
Right, so below 70%, or below the number, let's say below the number we have. So let me go switch to the calculator. And we want below 70 for the 70th percentile. And our mean was 16. I'm doing the fish problem. And the standard deviation was 2. And I want below. So 17, the length of the fish, that means 70% of the fish are below 17 inches long. And 30% are above 17 inches long. So that's useful information.
Mm-hmm.
So percentile always means below. And the number that we get on this calculator, we use the inverse normal calculator because we're given a percent. That number means 70% of the fish are below, are 17 inches long. 30% are above 17 inches. Okay, so does that help? And we could go back while we're on this calculator. We could go back and say, what percent or what's the probability the fish is 13, between 13 inches and say 20 inches. Well, that's too far apart. I went out of the range, so let's say 18. Okay, so that means I'm back at the fish problem. I'm asking, what's the probability your fish is between 13 inches and 18 inches long? It's 77%. So this time we have the numbers and we wanted to find the percent, the probability, or the area, which is all the same. So we use the normal calculator to do that.
Oh yeah, I was just about ready to ask. I think I would jumped over to the normal calculator to do that because you can plug in the between values.
Right. But on the inverse one, you can do between also. But it's a different between. It's different.
Well,
it's.
Don't you have to plug in the area to get on the inverse one to be able to plug in because those, if I remember right, the between values on the inverse they're not modifiable. You can't change those fields.
No.
Okay.
They're not. Because that's the answer. Those are the percentiles. They're giving you the answer. So the
Right.
inverse normal is giving you. I'm going to jump to that. You know the area, and if you want the middle area, that middle area is going to be between the two numbers. So if you want the middle, say 24%. And then those fish, the middle 24% of the fish will be between 15 inches and 16.6 inches long. This is the inverse normal one. So on an inverse normal calculator, you know the percent or the probability. On the other one, you're trying to find a percent.
I'm not seeing your screen. I don't know if anybody else is, but I'm not seeing.
I'm not seeing the screen either.
Okay, sorry. I'm going right there. Okay, here. So this is the inverse normal calculator, inverse normal distribution. So if I want the middle 24% of the fish, how long are they? So I know the percent, or the percent, or the area is 0.24. Those fish will be between 15 and 16.6 inches long. So if I know the percent or the area or the probability, I use the inverse normal calculator. If I want to find the area or the probability, I use the normal calculator. So almost all the problems in the homework, you have to decide which calculator to use. Is it starting to make more sense?
Yes, I'm just waiting for the central limit theorem.
Okay, let's move on to that then. And then if there's time left, then anybody else we'll go over something else. Okay, So, I think I'll just type this because I want to type a lot. So, central limit theorem. And I have clues on when you use this. This theorem measures how much the means of various samples vary. Okay, so what you would use this for, no matter what sample you're taking, whatever population you have, let's start with the population. No matter you have, it does not have to be normal. It could be normal, but it doesn't have to be. The sample means, if you take, no matter what samples you take, the sample means form a normal distribution. So a population, let's go back to, remember we did the basketball player wrap-up assignment. The population there was every single basketball player on the NBA. So no matter what sample we took, or how many, all the samples we took, their means of each one of those samples, because the sample's just a group, and the population is the whole thing. So the mean heights of any sample we took, if you put those on a graph, they would form a bell-shaped curve. The means would look like that. So, for convenience, the normal distribution is the mean, but we don't just use the standard deviation. We use the standard deviation and we divide it by n. But we do use the normal distribution calculator. Divide by square root of n, sorry. And sorry. Go ahead. More importantly, if you took the averages of all your sample means, so suppose you took 10 samples. If you found that means for each one of those samples and you took the average of those means, that would be your population mean. And this has all been proven and everything else, but we're not gonna prove this. So what I want to say is, here's what you look out for. If you want to do a problem using the central limit theorem, this is the wording you look out for. So the wording is assume the variable is normally distributed. Okay, now your population, a variable is not the population. Okay, if you remember from week 1. The variable is the number that you're looking for out of the population. So if we're talking about NBA players, the variable there is your height. So that's what has to be normally distributed is the variable. So in your problem, it'll say something is your variable is normally distributed, but the variable could be anything. It would be like, and I'll do example problem, but it could be heights, weights, I mean, anything. It's a number, okay? In the problem, you're going to be given. So you should look for these 4 things. You should look for the population it's coming out of, or the big set. You should be given an average or a mean, a standard deviation, and a sample size. So notice in every problem we did previously, there was no sample size. These things are coming out as samples. But in section 1, 2, or 3, we did not have a sample. We were talking about populations. And the question will be find, this is what it'll say. It'll ask you, find the probability the mean is, what am I doing? Find the probability. I'm sorry, I really have a hard time writing on this. Find the probability the mean is below, above, or between all right, so I'm going to do so let's look at let's just do number 1 in the homework. Usually I don't like to do a homework question, but we're kind of running out of time. So it's a soccer match. So the length of time, this is in 3.4. Length of time on one soccer match is normally distributed. So there's our variable right there. That's the first thing you look for. Our variables normally distributed. The length of time of a game. Okay, this is soccer again. The mean is 2 hours, so I'm given an average. The standard deviation is 0.5. The sample size is 50. So anytime they're giving you a sample size, that is your n, and you know to use the central limit theorem because you have a sample. So let's find the probability that the game lasts between 1.8 and 2.3 hours. So remember, this means between 1.8 hours and 2.3 hours. That's what that symbol means. Find the probability the game lasts between 1.8 hours and 2.3 hours. All right, I'm going to go to, I wish you could go and scroll pages, but you can't. So I'm going to do the mean and the standard deviation here in our normally distribution is 0.5, but we're going to use 0.5 divided by the square root of 50. That is the standard deviation over the square root of the sample size. So when we use our normal calculator, again, why would we use the normal calculator for this? Because what are we looking for?
That's what I was going to ask. What exactly is that? Because I'm with you all the way up until that point when because from what I was looking at in the Khan Academy, you know, we're just taking sample after sample after sample, you know, and basically getting another graph of how they all stack. But I still don't understand the square root. I don't understand what we're actually getting there.
What it's doing, it's translating. Since we can't, I can't show you, I can't prove this because it's it is all calculus.
Mm-hmm.
But the proof of the theorem includes that the best way to do this, since this is just one little sample, remember the central limit theorem says you take lots of samples.
Right.
Lots of samples, but we only have one little sample. So what this does, it like normalizes the standard deviation. Instead of 0.5, since we have such a small sample, usually it has to be over 30, but that's still small. We normalize that standard deviation by dividing it by the square root of the sample size.
So are you saying that by dividing that by the square root, it's basically performing like what he was saying, giving us the area or whatever, like basically a way of calculating 50 of the same samples? When you're doing that?
No, that just 50 means that there's 50 things in the sample space. There's 50 soccer games. That's what the 50
means. Oh, I
means.
see.
That there's 50 games in this soccer game because we're looking at the length of each of those 50 games. The only difference of this than what we're doing is we're going to divide these answers by the square root of n, the square root of the size of the sample space, because it normalizes it. We only have one sample. We don't have the population of every single soccer game. So we changed the standard deviation to make it more fit in with all the other samples.
So is this value now your standard deviation?
Yes, this is our new standard deviation.
Okay.
So we're gonna go to the normal. These are all normal. So we're always going to just be asking about the probability that the mean is between two numbers. So our mean was
0.5.
what was it?
0.5 or something?
No, 2 hours. 2-hour game.
Oh.
And our standard deviation, our new standard deviation is 707, and we want it between 1.8 hours. We want to know the probability that the mean, the population mean. See, we don't know the population mean. Sample mean, sorry, sample mean. And so what I'm doing here is the mean length of one soccer game, or the sample, okay, was 2 hours. We changed the standard deviation to normalize it because this is only one sample. We want to know the probability that the game, our sample mean, is between 1.8 and 2.3. So we want to know how far away from the actual mean of 2 is our sample mean. So we do know the mean. We know the population mean is 2. We're asking how far is our sample mean from what's the probability or the chances that our sample mean is between 1.8 and 2.3? And it's 99.77% that it's between those 2 hours.
So when we're working these out, we're basically using the square root of the population size. Like in that case, it was 50, and just plugging those numbers in
Sample
into
size.
the calculator.
Yes, it's the sample size.
I don't remember. I didn't hear who. Was it Charlie that said something a second ago?
Yeah.
I don't understand why we are using the square root, and maybe that's beyond my need to get through statistics, but why I mean, unless you have a brief, understandable explanation of why do we, to find this theorem, what is the value or what's the need of using that square root?
That is a really, really good question, and I promise, get an answer for you.
Yeah, because I feel like that would, if I
in
just
my-
get that, that'll hinge everything for that central theorem. Is once I understand why we're using the square root of the number that, you know, per problem, you know, whatever.
Okay,
Maybe
that's a
we
good
think
question.
I could go through the motions. You know what I mean? I can see the
know.
formula.
You wanna understand it.
I just want to understand
Right.
it, though.
Right. I totally understand where you're coming from. I will research that further and put it in words that we can all understand.
Well, you know what? Kind of the way that I'm going about it is that it's just a tool. I may not know what it is or what it's made out of, but it's to do a job. I just know learning how to use a tool. That's it.
Yeah. We just need to know how to use a hammer for a little bit.
There you go. There you go.
But the point of the central limit theorem for us, if you just regard where the square root comes from, because I will get you an answer. But the point is that you have the whole population mean, and then you want to know what's the probability that your sample mean is between two values, or is it above a value or below a value? And we use the normal calculator for that. But I promise I'll get you an answer about that square root.
I'll be honest with you. You know what really turned the corner for me? I'm sorry. The thing that really turned the corner for me was one specific question. Midway through this week, everything came together where it used the question about a home builder using a certain amount of days when they put it in construction terms, and what was the chances of completing early, on time, you know, going over. That's when everything made sense to me. That was, I'm not going, you know, yeah, that was kind of the tipping point for me. I understood what we were working with because, you know, my construction background.
Well, that's a real life problem. Yeah, it's not like how many apples you have, or, you know, I mean, it's a real life problem, and that's a really good point.
Yeah, I knew it was out there. Just needed to find the right one.
Okay, is there any other questions? Now, again, I'll be on in the morning, so if you want to, I'll try to answer it tomorrow. But if you run into anything that I didn't cover today, or even if I covered it, I can go over it again. Just shoot me an email, and I'll come up with some more examples.
Okay. I appreciate it. Thank you.
Okay, well, I appreciate every one of you coming on tonight. Have a good night.
Absolutely. Thank you very much. Have a great night, everyone.